Haskell is a functional programming language, which means that we work with mathematical functions, which take a given input and compute one particular output. And every time that you call the function, again, you get the same output again. Of course, we talk a lot about this in the Haskell Unfolder, but since today is our second anniversary, we are 2 years old today, we thought we would celebrate by looking at something slightly different and look at relational programming, where we don't have inputs and outputs necessarily, and we lose that distinction. And we're going to do this by looking at a very nice language called typedKanren, which is an embedding of a programming language called miniKanren in Haskell.
Welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed, so we invite you to submit questions or comments in the chat, and we'll try to put them on screen and discuss them.
Yeah, so if you've never heard of miniKanren, it's a programming language a little bit like Prolog, or quite a bit like Prolog, perhaps, which you might have heard of. And it's quite an active community. For example, the International Conference on Functional Programming, ICFP, in recent years has had a track dedicated to miniKanren. And this year in Singapore, it will also. And last year at this symposium, the two researchers, Nikolai Kudasov and Artem Starikov, presented an embedding of miniKanren in Haskell called typedKanren. And so today what I want to do is give you a bit of a flavor of what programming in typedKanren feels like. But there's no way that we can discuss all aspects of it, but hopefully you'll get a bit of an idea. So the main example that I want to cover today is a type checker for a small language. But before we look at this, a complicated example like that, let's first look at a few basics. So, like I said, we are programming with the relations. So rather than computing an output for a particular input, we're saying, like, what is the relationship between multiple inputs, or multiple values, rather? And so let's start with a very simple relation between two integers. And maybe all this relation is going to say is that these two integers must be the same. So how do we write something like that? Well, rather than working with integers, we're going to work with terms of integers. And a term of an integer is either known, we know what the integer is, or it's unknown, so unknown integer. And so this is a relation between two of those guys. And then the type of this whole thing, this relation, is a goal. Now, a goal is something that either succeeds or fails. And so we have two integers, two terms of integers, and we're just going to say that this must be equal. Now let's look at how we could actually run this. So we can run a goal. And so let's see what happens if we try to run example 1 with the integers 1 and 2. Now, these are not the same, so the goal is going to fail. And
so term of int is an instance of num?
Yeah, that's why this, that's right. That's why this is possible. Yeah.
Okay. So we don't have to explicitly embed the integers into
that's
the
right.
term type.
Yeah, that's right. Yeah, you could also.
But we could,
if you want. If you wanted to, you could do that. Yeah. But yeah, that's a good point. Yeah. Now these are not the same, and so we get the empty list, meaning no solutions. If we try 1 and 1, now these are the same, and so we get one solution, and that solution is trivial.
Is that the type of the parameter of the goal?
Yeah, so exactly. So this answer here relates to this parameter here. So let's look at some more interesting examples, because so far all we've done is a very complicated way of writing equality. All right, so let's now ask under which conditions for which x is 1 equal to x. And now we're going to get a solution saying, well, x here, that's again relates, must be 1. We can
so it was not the it was not the it was related to the type of the lambda, of the thing in the lambda, what you're getting out.
Yes.
Okay. But I was wondering whether it's like anything to do with the argument of the goal, which is a goal unit. But
here, no.
No. Okay.
We can also ask, what if for which x and y is x equal to y? Now, what it's going to tell us now is that we don't know what the value of x is, we don't care. We don't know the value of y is, we don't care, as long as they're equal. So it's this same meta variable, right? So this .1 here is a meta variable standing for some unknown integer, and we're saying that x and y can have any value represented by this meta variable as long as they have the same value. Okay, let's look at some other examples here. We can also use what's called as disjunction, this or that. All right, so let's look at the relation with one value, so a one-term relation or predicate. We can say that we just have an x here, and we can say x must be equal to 1, or, oops, x must be equal to 2. I seem to have lost the ability to type. Okay, so 1 or 2.
That's a common side effect of logical programming.
Is that right? I see. Oh dear. That might be harmful for my career. Anyway, so let's see some examples here. So what happens if we run this with the value 1? Well, it tells us there's a trivial solution, right? If we run it with the value 2, well, that's also a trivial solution. If we run it with the value 3, there are no solutions. 3 is not equal to 1 nor equal to 2. And if we ask for which x does this relation hold, does the predicate hold for x, well, then we get 2 solutions, 1 or 2.
Nice.
And the final example I want to show in this sort of basics part is that we can also have conjunction, right? So disjunction is this or that. Conjunction is this and that, right? So here we could say, well, and this is in Haskell embedding, this is done just through the monad instance. So we can say that x must be equal to y, and y must be equal to 1. And now if I ask for which x and y does this relationship hold, well, it tells me that both must be equal to 1, and this is the only solution. And in this case, it doesn't matter if I first say that x must be equal to y, and then say that y must be equal to 1, or the other way around. Oops. Jesus. That really makes no difference. All right, we're just stating requirements on these variables. Okay.
And can terms be recursive? So, like, could I don't know, write like example 2, a variant of example 2 that basically says x is equal to 1, or x is equal to 2, or x is equal to 3, but recursively? So, like, to any natural number?
I guess.
Sorry, just asking random questions here.
So, I mean, I guess we could write something
yeah, exactly. X is equal to n, or example 2 of n plus 1x.
Oh,
now you have to explicitly embed.
Now we have to inject, embed. I forget what it's actually called.
I don't know. From integer would work.
No, so it should be inject here. Okay, sorry, I was right. There's a prime missing. Sorry. Yeah, this will also work. Now, I think so, at least. So let's try. So now, of course, there's going to be lots of solutions. So we can ask for a few of them. Let's take the first 10 of run. Find me all x for which example 2 0. Let's start with 0. X holds. And it's
very nice. Okay, yeah. So I was wondering that so these are lazily produced, as you would expect. So
that's
very
right.
nice.
Cool. Yeah, and in fact, one of the differences between miniKanren and Prolog is the way that this search works, or at least, well, most Prologs use a depth-first search, and miniKanren usually is based on a breadth-first search. But
that's not really making a difference.
That makes no difference here, but it does make a difference in when you talk about
in general.
Okay. So the other thing to note about terms here is that terms of an integer is kind of an all or nothing thing, right? We either completely know the integer, we know what the value is, or we don't know anything about the integer. That's not always the case. And so I want to show that in the context of the real example that we don't talk about is a type checker. So we're going to have a type checker, and the types that we're going to infer are this type language, right? So we have integers, booleans, and functions.
Mm-hmm.
Now a type could be completely unknown.
No polymorphism.
No polymorphism in the host language.
Mm-hmm.
Yeah, that's right.
Mm-hmm. Yeah.
So
a remark, not a question.
Yeah. So a type, we have more possibilities, right? A type could be completely known. We don't know anything about it, or we could know that it's an integer. We could know that it's a boolean. But if it's a function, there's more possibilities, right? We might know that's a function, but we might not know what the arguments of the function are, the domain and the codomain. And so we have more possibilities than with integers. And so in the typedKanren library, this is called the logic version of the type, and we can derive it. We can say make logicals for type. Now this is a bit of template Haskell, and I can show you what this spits out. It spits out something like this. So the logic version is like for integers and booleans, nothing's changed. But for the function, we have recursive occurrences of term. So again, this could be unknown or another logic type. So this allows us to specify.
And then a term of type is defined how?
Yeah, so that's a good question. So a term of some type is either a variable with some internal representation, or a value of the logic variant of the thing.
Right. So in particular, term of type is either a variable or a thing of this logic type, data type.
That's right. Yeah, and so that's where exactly, and that's where the recursion then comes in here.
Yeah, exactly. Okay. Yeah.
Okay. We also want some show instance for this derived type, so we can just ask for that. Okay. Now this is the type language. We also, like, if we're doing type inference on what? So we need some sort of core language, and for that I'm going to have a very simple language here, which is basically lambda calculus with some constants. So let me just paste that in and then briefly discuss. So our expressions, this is what we're going to do type inference on, are either variables, and a variable is just a name, right? Just a bit of text. Application, right? One expression applied to another one. Abstraction, lambda abstraction, right? Lambda xe, or a constant. And which constants do we have? We have integer constants, Boolean constants, check if something is 0, and conditionals if. And so what we want is some function that, goes from, like, some type checker that goes from an expression to a type. Right? This is what we end up with. But we're not going to write it as a function. We're going to write it as a relation, a one-place relation. I'll come back to that at the very end. So,
a one-place relation on the type, I guess.
On the type, yeah. Meaning, under which conditions is this type the right type for this expression? So we're going to have an expression, and we're not going to compute a term here. Instead, we'll have a term of a type, and that's going to be a goal. Now, we'll see in a second that if there are variables in the type, well then, like, we don't know what the type of those things are, right? And so we need to have some way of mapping variables to types. That's usually known as an environment. And so I'm just going to define this as a mapping from variables to types, terms of types. Right, so a variable might also have a completely known type, completely unknown type, or a partially known type. Okay, so at the top level, there are no assumptions about any variables, so we can start with the empty environment with this auxiliary function here. This type environment is going to be our main function here, where we take an environment, an expression, and then we have a predicate on types.
Yeah, so this is actually cool, right? I mean, like, we've already seen this when we did this recursive calculation on the integers, but I mean, so you can sort of like use the power of Haskell, right? That's like the typical thing about embeddings, of course, but you can use the power of Haskell to construct these goals, right?
Yeah, exactly. Yeah, that's something that I think is very powerful about the embedding of miniKanren and Haskell. We really are combining functional programming with relational programming. Right? Given these inputs, we are computing a relation, and then we can solve that relation, see if it's satisfied or not, using the typedKanren library. So yeah, I think that's really nice. I agree. Okay, so how do we implement this function? We're going to pat the match on the expression. We're going to see what kind of expression do we have here. Now, if we have a variable, so we're always thinking like under which conditions is t the type of this variable, right? That's what this means to be a relation. Well, our environment tells us what type we are expecting every variable to have. So we can just look that up in the environment. And then we say that this must equal the type that we're looking for. I'm just going to have a catch-all case here for. Now we could worry about like if this is not actually in the map, and we could fail in that case. I'm just going to ignore that case for now. But
so for the time being, we're assuming that we're type checking closed terms in the end.
Yeah.
And then,
there's some sort of renaming stat has happened or something like this. Okay. Now, application gets already a lot more tricky. So we're applying some function f to some argument x, where both of these are expressions. Now, under which condition does f apply to x have type t? Well, f must be a function, first of all, otherwise we would not be able to apply it to an argument. Okay. If it is a function, it must have an input and an output, right? A domain and a codomain. The input, the type of the input, must match the type of x, this expression here, otherwise it would still be type error. And the result of the function must then be t. Okay, so how do we actually say this? Well,
so we need new variables somehow.
Yeah, exactly. We didn't say that this must be some function, okay, from something, like a variable, like Andres said, to t. Okay, we can do that. That's called fresh. That's the other feature of gold that I haven't shown you. Actually, there's one third, which is disequality, which I'm not going to talk about at all. But yeah, those are the three features of the gold monad: equality, disequality, and fresh variables. Okay, so now we have some fresh variable. We can now say that in the environment, which we have no new variable, so we can use the same environment here, f must be a value, meaning, right, not a variable. We know something about what f must be, which is a function from what? Well, we don't know from what. That's the a, right? To t. That's expressing exactly what we said earlier, right? It must be a function from something to the type that we're expecting here.
Which itself could be a variable, right?
Yes. Oh, yes. Yeah, definitely. Yeah, for sure. In fact, it typically will be. Okay, that's one thing. We also need to check then that if this is a function from a to t, that x better have type a. Right, and that's the only thing we need to do here. Okay, what about lambda abstraction? Now, lambda xf, where this is some sort of expression, and this is a variable name. This has type t under which conditions? Well, t must be a function from something to something, right? Where we don't know anything about those something. So now we need two fresh variables. And we can say that t must be a function from a to b. Right? If it's not a function, then this doesn't type check, right? Abstractions are always functions. Okay, but now we should check something about the body of this function, right? So if the function is from a to b, then in the body of this function, variable x, the argument of the function, is going to have type a. And then we should check that the result of the function has type b. So we can say, if we extend our environment where x has type a, then if we check the body, it should have type b. And that's it. And then for constants,
and again, are you saying that do we have to think about in which order we're doing these two things, like the t equals value and the recursive call? Does it matter for efficiency, or is the search algorithm such that it never matters? Or
so it doesn't matter semantically, but you phrased your question very carefully. You said it doesn't matter for performance or efficiency, and the answer is yes. The way that you order these things can very much make a difference to how fast search is and whether search will terminate at all.
And I mean, like, okay, so I don't know, 25 years ago, I programmed some Prolog. It's that long ago. Back then, I had a little bit of an intuition for like in which order you have to put things for the Prolog search algorithm. But you said that the algorithm of Kanren is different. So, what like is there any advice you can give, or?
I would say the specific requirements like this, where you say this value must have some concrete structure with no further recursion or anything. Do those as early as possible, so that we can make as much known as early as possible. And recursive calls like this, which don't immediately generate new information, do those as late as possible.
Okay.
Yeah.
Okay. Good.
Okay. So finally, we've delegated for constants to an auxiliary function here. So let's write that auxiliary function. Oh, we don't need the otherwise case anymore. And so we're going to do something very similar here. Constants don't have variables inside them, so we don't need the environment here. We're going to start the same way. Now, for the integer case, Boolean case, and is0 case, this is very simple. So I'm just going to paste it in. If we have an integer constant, well, then the type must be int. If it's a Boolean constant, the type must be bool. If the constant is 0, then the type must be the function from int to bool, right? So this is all very concrete, no variables inside.
So this we could also write using inject, right? If we wanted to, because there are no variables here.
Yes, you could have written inject t int here.
Yeah, okay.
If you preferred, yeah. That's right.
Yeah, I mean, for the function case, it's like three applications of value which all have logic in there. So I would be
true. Yeah.
Inject t fun t int t bool would be shorter, right?
Yeah, sure.
Yeah. Okay.
However, the conditional case is more interesting because what is the type of if? Well, it's bool to A to A to A for any A. Right. So now we need a fresh variable because every use of if basically, is for some unknown A. Right. So once we have such a fresh thing, and now we can't use inject anymore, at least not that easily, because now we have partially known information. Right. We say that t must be a function from bool to A to A to A. Right. And this is a little bit awkward because this is all curried, of course. So it's bool to A to A. Oops, what happened? Bool to A to A to A, which is bracketed like this, right? That's why this looks a little bit awkward here.
Do you have time for a question from the audience?
Go for it.
From Nicholas. Is this a library, or is this library written in pure Haskell, or is there interop with a different language?
No, this is pure Haskell. There's no, this is an implementation of miniKanren. It doesn't call out to an external interpreter. Okay, and that's it. That's our type checker done. That's all we need to do. So let's see some examples. Let's see how this works. So we're going to get solutions out of this when we run this, and those solutions are terms of types. So let's see. If we have the constant 1, we're asking for which t does the constant 1 have type t? Right. So this is the question about type inference.
So we would hope integer, right?
That would be reassuring. And indeed, that's what we get. Right. It tells us this is an integer. Now, just to make a little bit later examples a little bit easier, if we look at this, this is like lambda t type of something t. So we can just remove the t argument here and remove it here also. Right, this is, I hope that's clear to everyone. It's just
eta reduction.
Eta reduction, yeah. So this is the exact same thing, right? It doesn't really matter here, but it'll matter a little bit later. Okay, let's look at a more interesting example. So let's ask, what is the type of lambda x?
Yeah, so now I said there is no polymorphism, but we get sort of this meta level. We expect to get meta level polymorphism here, right?
Yeah, exactly. Our type language doesn't have variables, right? We can't say for all A to A, even though that's the type that we would expect. We can only choose int, bool, or functions. But indeed, these are terms of types, and so we could have partial information about those types. Right, so now if we look at this, indeed, it tells us this is a function from something to that same something. Right, which is really for all A to A. Right, so you could definitely, if this was part of a larger project, you could take such a term of a type and construct what's called as a type scheme or a polytype out of this, where you look at all the variables that are still uninstantiated and universally quantify them, like for all.
What operations does typedKanren give us on this var thing? Like you have equality, I guess. Do you have like OR instance as well, or something like that? I mean, I guess we cannot really do much more, I would suspect, right? Because you are not supposed to, like, I mean, but I would hope we can check them for equality, right? I mean,
we can. Yes, we can. Yeah. We have show and eq. That's basically it.
Okay.
Yeah. Okay. Let's look at a slightly more bigger example. I'm just going to paste it in here rather than type it all out. So what is this here? Lambda x, lambda y, and we're going to apply something. We're going to apply this to that. Okay. What are we applying? We're going to apply if to another application is 0 of x. So if x is 0, then y. Right, so this is lambda x y if is 0 x y.
Okay, yeah. So it's still a partial application of the if.
That's right. It's a partial application of the x. So this should be the same as lambda x y z if is 0 x y z, or indeed the same as this. Right, and so what do we expect to happen here? Well, if I look at the fully qualified version, where the z is not really present in the actual term, well, x, we're going to apply the function is 0 to x, so that means that x must be an int, exactly. But if doesn't say anything about the other two arguments, right? As long, but it does say that must be the same. And so we expect for this whole thing the type bool to A to A to A. Right, bool to A to A, the same as int itself. So that's sorry, not bool, int.
Sorry.
To check if it's int, that's 0. So let's try example 3, and we get function from int to something to something to something. Right? So that's exactly what we get. Now, if we have a minor variation on this example, which shows this is the same example, except that Anders just said that we were still missing the z, right, in the previous example. In this example, that z is not missing, but it's not an argument, it's a constant. It says true here. That's this guy here.
Okay, then this should be into bool to... Oh, well, 2 arguments now. Into bool to bool, right?
Into bool to bool, exactly, yeah. So exactly. So that's z argument is gone, and this, since the 2 branches of the if must be the same, we're forcing the type of y to be the same, to be bool. So let's look at that, and that's exactly what we get: int to bool to bool. So with very little work, we wrote a pretty sophisticated type checker, which I think is quite nice. Now, before we wrap up, I want to show, and I'm just going to show this very superficially. You can look at all these examples will be, as usual, in the Unfolder repository, link in the video description, as is, by the way, a link to the typedKanren library and a paper on typedKanren from last year's ICFP track. Anyway, so you can look at the details there. But I just wanted to show you that, so here we had a one-place relation, right, like a predicate on types. We could also write this as a complete relation, right? So a relation between environments, expressions, and types. So this is now a 3-place relation, a ternary relation between all kinds of things here. And then if you look at the definitions here, like there's a little bit more of boilerplate, but not all that much. typedKanren, I think, does a pretty good job at making this kind of thing quite pleasant to write.
So then if you've ever seen sort of such a type system written as these type rules, then this is basically
this is
more or less a direct transcription of those rules.
That's right. That's right. Yeah. Inference rules. Yeah, exactly. Yeah. So this is quite nice. Now I'm just going to load this here. Type checker.relational. Now we had
stuff which we haven't seen, like match E and on.
Yeah, that's right. There's a little bit more happening here that I won't have time to talk about this, but this is basically the relational equivalent of pattern matching that we did here with an actual pattern match. Here we can't pattern match because we don't have an expression, right? We have a term of an expression, which might be this partially known thing, right? So that's why pattern matching in our case is impossible. And this this is part of the library that we haven't had a chance to talk about, but it's described in detail in the paper. The one thing I did want to show is a consequence of writing this as a relation rather than a function here. So we could, of course, do the same thing that we did before. So I have the same examples here that we discussed, like examples 1, 2, 3, 4. So if we just look at example 4 here, we still get int to bool, right? So this is the same. But since this is now a relation, we can also go the other direction, right? We can say, well, which expressions have type bool, rather than which types. For which types does this expression have this type? We're now asking for which expressions does this expression have this type here. So we're asking for expressions that have type bool. So now there's going to be lots of those, of course, and so I'm just taking 5 of them just to avoid infinite meaning, and let's just print them like this so we can clearly see what they are. And so let's see. A Boolean constant has type bool. Okay, that makes sense. If we apply is0 to some integer, like whatever the integer is, that has type bool. Okay, that makes sense. And then we see a bunch of other examples where we have a abstraction here, a lambda abstraction, that takes some argument, then ignores that argument, and just gets you a Boolean constant back. So it doesn't matter what's here, right? All of these are going to have type bool. And similarly, we could also ask for expressions of, for example, int to bool. And if we do that, we're told, okay, well, is0 has type int to bool. Okay. An abstraction that takes some integer and returns a Boolean constant has type int to bool, right? And so forth. So we could run this in either direction, from types to terms or terms to types or types to terms, which I think.
And you said you made it a 3-place relationship, so we could in principle also ask for environments, right?
Yes, you could.
Yeah,
you could
say like in which environments could this be type checked, and then you would get something like it has to have at least something for the free variables or something like that.
Yeah, that's right.
I mean, I hope. I don't know.
Do you want me to try that?
If you want.
Okay, that's risky. Let's see. Right. Okay. So type. I haven't actually tried this, so let's see if I follow my face here. Type in env. So for which environments does, say, the variable x, I need to inject this, have type tint? Oh, what did I do?
Inject prime.
I need to. Sorry, this is a separate import here. Oh, wait. Okay, sorry. I need to.
Yeah.
No. Okay, we get some answer here. No, well, here we go. It says the first solution is some environment in which X has type int, and then whatever else is in the environment. So there you go. And it also tells us the second option here is that, okay, there could be some additional variables.
X is not appearing.
It could appear somewhere else in the environment. Yeah, exactly. It doesn't have to be the first thing in the environment. And so all of these examples are like it appears somewhere.
I'm just surprised now, but like because if the variables are completely unconstrained, could it not be that there is another binding for X, which then says that it is of type bool?
No, but that's a consequence of. So this is one of the. I'm using.
You're using this equality.
to say that yes, exactly, yeah.
Oh, okay. Interesting.
So this is a good use. I think this is one of the typical uses where disequality becomes quite useful. Okay, are there any questions?
You're requiring that the bindings in the environment are all disjoint, or what does this say?
No, it says that once x has a value, that we don't keep looking for x down in the rest of the environment. Like if you see an environment where x is at the start, then the type of x according to that environment must be that binding, even if there's additional bindings.
But then I'm still surprised, because if in the second line .2 is x and .3 is bool,
oh yeah,
then
okay,
this would actually be a solution, right?
Yes, true, fair enough. So I think that's because, and I think this is a limitation of the library. I think this is to do. Here we should really have, in addition to the solution, and then disequality constraint saying, and by the way, x cannot be this 2 cannot be x. Other implementations of miniKanren will tell you that. typedKanren currently doesn't tell you that. I don't know why. I think that's just just an easy to fix to do. It just doesn't tell you that at the moment. But yeah.
Okay, so there is one more question, again by Niklas, which is, how is the goal type defined? In particular, how does it know how many variables to pass into the lambda? And Niklas clarified, I mean the lambda passed to run.
So it doesn't, I mean, the goal, like the internals of goal is quite complicated. Look at the paper for that.
Sorry, go ahead. You know better than I do. Yeah.
Well, I was just going to say, it does not know how many variables to pass. So you decide, right? So you pick the argument here. So you could pick, whatever.
Exactly.
But you decide what you put here.
So there's some kind of overloading for this run function, which allows you to basically put any tuple type there, or possibly even other types which contain variables.
Mostly just tuples, yeah. So it's basically anything that has a fresh instance, which is basically just any tuple of terms. It's the same mechanism that allows you to say things like A, B is assigned fresh. That relies on the exact same instance. Yeah.
Very cool.
Anything else?
There's a follow-up question. Does that work without fancy extensions? I think that in itself is just like normal type class overloading. I mean, so that's relatively unfancy, right? I mean, so probably if you look for the type of run, you'll see this fresh instance constraint showing up, right? You can probably just show the type of run. And then if you look at like :I fresh, you probably see that there are instances for various different tuple types. So it's I think, yeah. So this is, I wouldn't call this particularly fancy.
Yeah, for the whole library, it depends on what you mean by fancy. It depends on type families. It uses template Haskell quite a bit, but that's, I don't know, it uses some generics to under the hood.
The template Haskell is optional, right? I mean, like
in principle,
in the sense that, like, I mean, it's really convenient because you don't want to write these logic instances by hand, but you could.
If you wanted to skip the generics and skip so write everything by hand, then I think in terms of fanciness, the most important fancy thing is associated types, so type families. Okay. If there are no other questions, then I guess we'll wrap up.
So thanks for watching this episode of the Haskell Unfolder. I hope you enjoyed it. Please like and subscribe. And as usual, we'll keep the chat open for a few more minutes. But if after that you have any more questions or comments, please leave them in the comments below the video and we'll try to answer them there. And see you again in a few weeks.